Okay, so now we're actually going to solve polynomials, but I'm not going to give you one of the factors. We're going to have to figure that out on our own. So there's a couple different theorems and rules that we need to learn before we do this. The first one is the rational root theorem. That's the first one right here. The rational root theorem, I know this is a lot of words, and this is the formal definition. So what it's really saying is if we have a function called f of x, then we can take p over q to figure out all of the possibilities for the roots. So p over q is really important. You need to know this right here. This is how you figure out possible roots. This is how you figure out what to try with synthetic division so we can figure out where to start. Now, what is P and Q? P is a factor of the constant. Q is the factor of the leading coefficient. So know what they are. Okay? P is the factor of the constant. Q is the factor of the leading coefficient. So you put those above each other, and then you actually do the plus and minus of each of them. Okay? So we'll use that here in a minute. Now we also have the fundamental theorem of algebra, which we've already kind of talked about. The fundamental theorem of algebra says you have exactly n roots if for a sub n, or a to n. Okay, now what does that mean? That means the number of roots is the same as or equal to the highest power. So if you have an x to the fourth polynomial, you have 4 roots. If you have an x to the fifth polynomial, you have 5 roots. Now, some of those roots might be complex. All of them might be complex. Some of them might be the same. We could have a triple root at one number. We could have a double root at one number, which means 2 is a root twice. But then we also have, or we could have all different ones. Okay, lots of possibilities. Now we also have Descartes' rule of signs. I never say his name right. Descartes' rule of signs is another tool that can help simplify what all we can use for synthetic division. It's going to take that giant pool of possibilities to use with synthetic division, and it's going to help us cut it down so that we have less possibilities. It's going to make this a lot faster process than just guessing and checking. So with Descartes' rule of signs, we can figure out what types of zeros we have. So what you want to look for is sign changes. Okay, so for f of x, we go from a negative to a positive. Does the sign change? Yep, sure does. Then we go from a positive to a negative. Did the sign change? Yep, sure does. Then we go from a negative to a positive. Did the sign change? Yep, sure does. So this means we have 3 possible real zeros. Now here's the deal though. You're going to take that 3 or whatever number it comes out to be for that, and you're going to subtract it by 2. So, or we have 1 possible real positive. Oh my goodness, I can't talk today. Or we have 1 positive real zero. Okay, so if this came out to have 5 sign changes, you could have 5 positive real zeros, 3 positive real zeros, or 1 positive real zero. Okay, now you also have to check for f of negative x. So now we're going to check to see if any of the zeros are negative. So f of negative x means we plug in a negative x for each of those. And then we simplify it down. So this comes out to be a negative x to the third. Negative and negative is a positive. Negative squared is still a positive. Whoops, forgot this negative. Okay, so on this one, for f of negative x, do we have any sign changes? We go plus to plus, nope. Plus to plus, nope. Plus to plus, nope. So that means we have no negative zeros. Okay, so if we use that P over Q theorem, that would mean that we would take all of these possibilities for our that could be our factors, and we could really narrow it down. So let's look at that. So if I look at P over Q, P, remember, is the factors of 5. Q is the factors of the negative 5. So factors of 5, we have plus and minus. Let's start with 5. 5 over 5. We'd have plus or minus 5 over 1, plus minus 1 over 5, plus minus 1 over 1. But what do we know? We know that we have no negative zeros, which means when we start plugging into synthetic division, do we need to look at any of the negatives? No. So really, we can just say, all right, so it's either 5, 1, or 1/5. And we can start there. See how I really narrowed that down from what, 1, 2, 3, 4, 5, 6 different chances to 3. So that's Descartes' rule of sign. Now we also can set boundaries, which will also help break it down. So when we're setting boundaries, we have an upper bound and a lower bound. The upper bound is if there's no sign changes after synthetic division. So we're going to use synthetic division. Whatever we get, if the remainder is not 0 and all signs are the same, it's an upper bound. For the lower bound, it's very similar, except we're going to do synthetic division. If the remainder is not 0, which means it's not a 0, and the signs go back and forth, so negative plus, or plus negative, then it's a lower bound. Now, what does that mean? Okay, let's look at an example. So here's our example. Now, if we have this problem, I'm going to break it down a little bit. Okay, so P over Q, we would have factors of 24. So we have plus or minus 24 over 1, plus or minus 12 over 1, plus or minus 8 over 1, plus or minus 6 over 1, plus or minus 4 over 1, plus or minus 2 over 1. Okay, listed all of my possibilities. Now from those possibilities, that's a lot of possibilities, right? Factors of the 24 on top, factors of 1 on the bottom. I really don't want to do all of those. Well, first, you could use Descartes' rule, but we're not going to do that quite yet. We're just going to look at the boundaries. Let's say I try 6. So if I do 6 in the magic box and I bring down all of my lovely coefficients, I'm going to do this real fast here. Multiply, add down, multiply. Okay, where did I mess up? I didn't. 24, so 48. All right, so with 6, do you see how after I did synthetic division, none of them, our remainder's not 0, and none of them have a different sign. They're all positive. Since they're all positive, 6 is an upper bound, which means none of the zeros are going to be above 6, which means I can not even look at 8, 12, and 24 because 6 is an upper bound. Now let's say we look at some lower bounds. Let's say we look at -6. If I do that and then do our lovely synthetic division, bring that 1 down. 1 times -6, add down, multiply, add down, and then multiply. I think it's 3 something. So we're doing 64 times 6, 384, negative. And then we add down. So for the lower bound, look at this. We go positive, negative, positive, negative, positive, negative, positive, negative. So my signs are every other, which means that this is a lower bound. What does that mean? That means that we wouldn't have anything smaller than -6. So we wouldn't have -8, -12, or -24. So that really narrowed down my possibilities because it wasn't 6 either. So now it's either 4, -4, 2, or -2. These are the only ones we haven't crossed out. So you can really narrow down what numbers you plug in to synthetic division to solve these problems. Let's look at one, and we're going to apply all of these rules. So, what did we learn today? Step 1. Step 1, what was the first thing we learned? The rational root theorem, right? Find the roots. Step 2. You can either go straight into trying, guessing, and checking, or use Descartes sign rule. Step 3, you could even narrow it down further if you wanted to by using upper and lower bounds, or from there just start doing synthetic division and let's just see what happens. We can recognize upper and lower bounds if we know those sign tricks to cancel other stuff out. All right, so here we go. First step. We have P over Q's. So factors of 20 and factors of 1, because that's what would be in front of the x to the third. So factors of 20, let's see. We have plus and minus 1 over 1, plus and minus 2 over 2. Whoops, 1, my fault. Got ahead of myself. Plus or minus 3, 4, 4 over 1. And plus or minus 5 over 1. And don't forget about the 20. So 20 over, and 10. Woo, there's a lot. So there's all of our options for synthetic division, all options of factors. That's a lot. Let's see if we can break it down. Whoops. So if we come down here, let's see if we can simplify it a little more. So now we're going to do step 2. The sign rule. So with Descartes' rule of signs, we're going to look at that, and we have x to the third minus 5x squared plus 4x minus 20. How many sign changes do we have? We go from positive to negative. There's 1. We go from negative to positive. There's 1. Positive to negative. There's 1. Which means we either have 3 positives or 1 positive. Let's see if there's any negatives. So f of negative x. We would have negative x to the third minus 5 times negative x squared plus 4 times negative x minus 20. If we simplify that down, we get negative x to the third minus 5x squared minus 4x minus 20. The signs don't change at all, which means we have no negative solutions. No negative solutions, which means what? That means we don't have to plug in any of the negative numbers up here. So really, we only have to check for 1, 2, 4, 5, 10, and 20. I just took out my negatives. So let's try some. I like to start in the middle to see what happens. Let's try 4. So we have 1, negative 5 for our coefficients, 4 and negative 20. Bring it down. Multiply, multiply. Oh, well, that didn't work, did it? It's a positive that we plugged in, and it's every other sign, so it's not an upper or lower bound, and it's not a 0 because it has a remainder. So that was a no-go. All right, let's try another one. Let's try 5. That's kind of close to the middle. So I'm going to erase this. Put a 5 in my magic box. Bring the 1 down. 1 times 5 is 5. 0, 0, 4, 20. Hey, remainder of 0. What's that mean? That means that x equals 5. There's our first solution. What else does that mean? We started with an x cubed. Now we're down to an x squared. Oh, this is a pretty one. Look at this. You can literally subtract and square root. So x equals plus or minus 2i, which means our other roots are complex. So we have one real solution for this one, and that is a solved polynomial.